Okay, the purpose of this video is to practice making pH and pOH calculations. And there's actually a second objective here, because what I'm going to do in addition to that is show the relationship between pH and pOH. Because when we calculate a pH, we can also know the pOH, and because there's a relationship between the two concepts. So let's go ahead and start, and we're gonna sort of work two problems at the same time. So on this side of the screen we're going to be calculating pH, and over here on the right side of the screen we're going to be calculating pOH. For the pH calculation, what I want to do is calculate the pH of a 0.001 molar solution of nitric acid. That's HNO3. Remember that nitric acid is a strong acid, and I think I'll go ahead and label this. There are 6 strong acids, and if you're in a high school chemistry course through university level general chemistry, I highly recommend that you know all 6 strong acids by heart. And in previous videos of the playlist, I justified that because when you, one of the main questions that comes up from students is how you recognize the difference between a strong acid and a weak acid. And the easiest way to do that is by knowing the 6 strong acids. And when you see something that's not in that list, then there's a very good chance it's a weak acid. All right. Now, similarly, for the pOH problem, we're going to look at a 1 times 10 to the minus 11th molar solution of KOH. And KOH is one of your 5 strong bases. One of the 5 strong bases. Now, it's important in this presentation to know whether we're using a strong acid or a strong base, because finding the pH of strong acids and strong bases is easier than finding the pH of a weak acid or a weak base. And the issue of the weak acids and weak bases is will be subject matter for a different video. All right, now we're going to start with the pH, and what I want to remind the viewer of is that for a strong acid, you have 100% ionization when that acid is added to water. So I'm going to quickly write the chemical equation for that. So we have HNO3 plus H2O, and will form H3O plus the polyanion NO3 minus. And remember that you have 100% ionization. So whatever we put into the water, and in this case we're going to add enough nitric acid to make a 0.001 molar solution, that this particle, and I'll emphasize it with an asterisk, this particle is going to ionize completely. So after the reaction is over, there's going to be 0 of the HNO3 particle, and we will have produced 0.001 molar of the H3O plus and 0.001 molar of the NO3 minus. Now, another part of this is to recognize that the nitrate itself has no bearing on pH. So it has no bearing on the pH of the solution. And additionally, remember from other things that we've done that this base is a weak base. Strong acids have weak bases. All right. Now, let's go ahead and turn to the situation with the KOH. Remember, for a strong base, we have a similar situation. So we take the KOH, we add it to water, and the material is going to ionize completely to 100%. So, like with the strong acid, we're starting with a solution that's 1 times 10 to the minus 11th molar. And after the KOH fully reacts, there's going to be none of that particular particle left. However, we will have produced equivalent amounts of the potassium ion and the hydroxide. And the hydroxide is the animal, if you will, that's controlling or that has an effect on the pH and the pOH of the resulting solution. All right. Whereas, and I'll put an asterisk by it, the potassium ion has no effect on pH or pOH. That's an important thing to realize about this. It's all about the OH minus, and it's all about the H3O plus. Now, to find the pH of the acid solution, remember that by definition, that the pH is going to be minus the log, and it will be concentration of. Now, since this is a strong acid and it ionizes completely, we can know the pH by literally using the concentration of the initial acid. And this equation is therefore equal also to the concentration of H3O plus, and I'll show both versions here. So to find the pH of the 0.001 molar solution, we simply plug in the concentration of the acid, which is 0.001. And the pH, therefore, is going to be equal to 3. Now, for the base, it has a similar looking equation. It's going to be pOH is equal to minus the log. And then, again, remember from the previous videos in the playlist that KOH is a strong base. Because it ionizes completely, we can also find the pOH directly from the concentration of the KOH, the initial concentration of the KOH. So the pOH is equal to minus the log of the initial concentration, or, to be consistent, minus the log of the concentration of OH minus. Remembering that both of these things are equivalent. They're the same. And it has to do with the fact that the KOH ionizes to 100%. So the pOH of the 1 times 10 to the minus 11 molar solution is going to be minus the log of 1 times 10 to the minus 11th. And so the pOH of this solution is going to be equal to 11. Now, these two quantities are related to one another because the addition of the base and the addition of the acid is in water. And so what I want to do is show you how these two things are related. And to do that, we need to talk about water. All right, so water itself undergoes what we call an autoionization. So if we were to measure the pH directly of a sample of pure water, here's what you find out. You find out that the pH of the pure water is equal to 7. And the pOH of pure water is also equal to 7. Now, this autoionization, you can look at this, how does this happen? So to understand that, you really have to draw the Lewis formulas of the particles, which is what I'm going to do here. And there are 2 water molecules involved in this. You can see that from the balanced equation I wrote. Here's the 2. Remember, this just shows us the ratio in which things are reacting. All right, and we get one of these and one of these. So there's going to be 2 water molecules that are involved in this initial ionization. And remember from the previous playlist that ionization means the formation of ions, and you can see what we're forming is the H3O plus and the OH minus. Now, it's important when we talk about how this happens to remember the relationship between the oxygen and the hydrogens in the water molecules, because the oxygen is electronegative by comparison to the hydrogen, and that means that the electrons that are shared between the oxygen and the hydrogens are not shared equally. They're in fact hogged by the oxygens. So the electrons are withdrawn towards the oxygens, and that puts a partial negative charge on the oxygen and partial positive charges on the hydrogens. So this is the way. This shows the relationship between these two molecules. So what can happen is that a pair of electrons on the oxygen can actually abstract the hydrogen from a neighboring water molecule, forming the H3O plus and the OH minus. Now, in reality, the concentration in pure water of the two ions is 1 × 10 to the -7th for both of them. And if we multiply these two values together, so we take the product of these two things, their product is equal to 1 × 10 to the -14th. And what's important for the viewer to understand is that this value, 1 × 10 to the -14th, is actually constant under all circumstances as long as we're at a fixed temperature. So I'm going to rewrite this as 1 × 10 to the -14th. Oh, excuse me, got a little typo there. Let me redo this very quickly. So we're going to rewrite this as 1 × 10 to the -14th, and it is equal to the product, square brackets, all right, and remember what the square brackets mean. They mean molarity, so the 1 × 10 to the -14th is going to be equal to the molarity of the H3O plus times the molarity of the OH minus. Now, if we take the log of both sides of this, then we get a new relationship that I'm going to put over here. All right, and that relationship is going to look like this. It's going to say 14 is equal to the pH plus pOH. So now, if we go back to our example, notice that the pH or the pOH of our solution here was 11 for the base, and the pH was 3. So if we pull these down now and we sum them together, notice that the pH of the solution that we started with this example was 3, and if we add that to the pOH, which was 11, notice that what happens is we get 14. So the aim of this video initially was to teach you how, or to show you some examples of how pH is calculated for a strong acid, how it's calculated for a strong base. The secondary objective was to point out these following relationships, which we're going to need in the subsequent playlist, that 14 is equal to pH plus pOH, and then in terms of concentration, 1 × 10 to the -14th, which is a constant, is equal to the product of H3O plus OH minus. And in finishing, we're going to call this constant, this 1 × 10 to the -14th, what is called the Kw for water. Capital K with a little w here to indicate that this constant has to do with the ionization of water into H3O plus and OH minus. And with that, I'm going to close the video.